In this problem, we need to determine the number of good nodes in a binary tree. A node x is considered good if there is no node with a value greater than x on the path from the root to x. Essentially, we are looking for nodes that are greater than or equal to all the nodes encountered from the root to that particular node. To solve this, we need to traverse the tree and check each node to see if it's good. During the traversal, we keep updating the maximum value encountered so far. This allows us to determine if the current node is good by comparing its value with the maximum value seen on the path from the root. We use a recursive approach to handle this traversal effectively. We start with a function named goodNodes, which initiates the recursive process with the root node and its value. The main recursive function, countGoodNodes, is responsible for checking if the current node is good by comparing its value to the maximum value encountered so far on the path from the root to the node. If the node is good, meaning the value in the node pointed to by node is greater than or equal to maxval, it means its value is at least as great as the maximum value seen up to that point. When this condition is met, we mark the node as good by setting good to 1 and update the maximum value to maxval equals the value in the node pointed to by node. Next, we call the countGoodNodes function recursively for both the left and right subtrees. We add the number of good nodes found in these subtrees to the current count. This recursive call is done using this expression. By recursively traversing the tree, we ensure that all nodes are checked and counted if they meet the good node criteria. This recursive approach is very effective for this problem. The function countGoodNodes starts with the root and traverses down the tree. For each node, it checks if the node's value is greater than or equal to the maximum value encountered so far. If it is, the node is marked as good and the maximum value is updated. This process is repeated for each node until the entire tree has been traversed. In summary, this algorithm effectively traverses the entire tree and counts the good nodes by comparing each node's value with the maximum value encountered on the path from the root to that node. The recursion handles the traversal and comparison efficiently, ensuring that each node is processed only once. This approach guarantees an optimal calculation of the number of good nodes in the given binary tree. By maintaining a running maximum and using preordered traversal, we ensure that the solution is both straightforward and efficient. This method not only meets the problem requirements, but also demonstrates the power of recursive tree traversal in solving complex tree-based problems. Now, it's time to put this implementation to the test. Don't hesitate to experiment with your own ideas and explore other potential solutions to the problem.